I'd like to open the floor up to any questions anybody might have. We'd like to have a good active panel discussion. Please go ahead and grab a microphone and toss a question at one or more of our presenters. Anybody? I see no hands go. Oh, John, I knew John would do. Yep, we got another one coming from the back. Great.
Joe, at the beginning of the conference, we were talking about deployment of research and getting it to the field. So from an end user's perspective, what is that secret sauce of getting research into deployment? And can you comment how long it takes to get there?
That's about as loaded. It's about as loaded of a question as you can get. The secret sauce is really coordination between the owner, the researcher, and some commercial applications. So take, for example, the NETC that was done. That was done with 5 states through New England as a pool fund study. We had 3 manufacturers participate. Kenway Composites, now a division of Creative Composites, was one of them. And we had a very interested and very knowledgeable research institution to do it, who had a vision that at least was practical. It was a solution for a problem, not a solution in search of a problem. So it's more of keeping everything kind of founded in reality. It's the way I have to say it. And making sure you have all of the partners involved. It just can't be a state thing. It can't just be a research thing. You have to have the commercial aspect as well to make sure that this is still viable and will survive after a 1-off, 2-off experimental project. In time frame, 2 to how many years are we in the G-beams now?
3.
So yeah, 2 to 4 years is really more practical application from inception of project, developmental research, experimental projects, and then kind of make it more mainstream.
Hi, gentlemen. We know there's a lot of emerging concerns regarding like chemicals such as PFAS and other environmental components such as that. So can you speak to some of the risks that may be present, especially in the environments that are changing, like the oceanic installations and things such as those? Are there no risks at all? And how will we communicate that to the public?
Well, at least, so when you get a thermoset resin, once it's done, it's done. It's completely inert. It'll never leach anything. It is what it is for infinity. And as part of, as you saw, some of the stuff that we're doing with the pier stuff and retrofitting, while we're not doing it structurally, you can also apply it as a structural repair and increase things to survive some of the more extreme environmental events that have been more everly present in the last couple of years.
With the materials we have worked, and as Joe mentioned, first the thermosets and then we'll add the thermoplastics, we have no evidence that they can lead to any type of contamination of the environment. One interest that we have is to work with bio-based materials in all those applications that are possible, that are feasible. And again, we are looking at materials that after the use, they can be recycled, if they can be somewhat compounded into a new shape, a new form. It is certainly a very important consideration. Think that what we can do is we can prevent other issues that are known with other construction materials. So like, for example, we can avoid the use of treated wood in applications where the treatment, it is known in many cases to be a contaminant. I mean, if we can use materials that are durable and with that need of chemical treatments. So again, we are very attentive. We will certainly report or pay attention to any evidence we find, but so far, personally, I don't have concerns based on our experience.
Thank you.
Yeah, I'd add just one other thing to that. Roberto mentioned in his talk that with the thermoplastics, there's very little off gassing. They're very clean in terms of working with them. And we've also got direct evidence that what we're getting is exactly what's coming out of the bar. We're not, or what's in the bar. We're not leaving anything behind. But longer term, the thermoplastics offer the potential for recyclability, which is potentially very useful, right? That's the one downside to a thermoset, or one downside to it, not the one, but one. That can't be broken down chemically. Like Joe said, it is what it is. And when you dispose of it, you kind of have to dispose of it unless you find some sort of in-kind reuse. Whereas the thermoplastic, you can actually melt it and reuse it in some other form. So that's an environmental benefit. The other thing we always have to remember with all this stuff too, is we're talking about infrastructure. So we're talking about things that should be lasting, 100 years or more with minimal maintenance. So when I think about environmental concerns, I always worry a lot about plastic bottles that don't get recycled, and containers and things like that, single-use items that go right into the waste stream. And we always have to keep in mind that with our applications, that's really not an issue. Even if the part is big, the part's going to be there a really long time and serve an important purpose. And as we've seen in some of our talks earlier, there could be other environmental benefits in terms of carbon capture, reduced energy use, and things like that really should be weighed in the equation. So.
Yeah, I absolutely agree. I think, it's a really important consideration, the circular economy component of it. And then there's a lot of good application too, I think, in the future for some habitat sort of environmental mitigation there for some of our concerns into the future. Thanks.
One thing I would add to that quickly is the Bill and Roberto mentioned thermoplastics are recyclable and repurposable. The material that we use to make the rebar that you guys have on your tables started out as PET water bottles, like a Poland Orange bottle or a Coke bottle. The manufacturer actually recycled those bottles, added a modifier to them, and created this material.
Here in.
That wasn't here. Yes, I'm sorry. The manufacturing of the material was here. Yep, in Colorado.
Oh yeah, you mentioned that. I apologize.
Any other questions? Yep, thanks.
My name is Balaji, graduate student from URI. So I have a question regarding the glass transfer temperature of the PET-G. So when concrete gets heated and let's say it's very sunny, right? Its capacity stores so much heat and the temperature gets close to the glass transition. So at that point, it starts becoming rubbery and stretches. So accumulated heat will cause the bridge to start sagging, because of the plastic is getting weak and it's rubbery. So how do you stop that plastic from sagging due to the rubbery as it hits the glass transition temperature?
That's a good comment. The evidence we have that the temperature of concrete that reaches during the curing reaction is well below the glass transition temperature of PETG. So, but it can be an issue with other polymers. I mean, that's a very important check to make. In fact, that was in a related project when Joe mentioned about the 3D printed forms for the railroad bridge for precast concrete. That was a consideration there because a different product, but in that case, we look carefully at the glass transition temperature of the polymer. The polymer used in that case was ABS in that 3D printed application. Again, we are always with the glass transition well above the temperature in concrete during the curing reaction.
One thing to add to that, though, that we have to acknowledge, though, is, and we saw it with the collapse of the bridge in Philadelphia, right, is heat and fire due to fire. And that is something that's an unavoidable fact of life with thermoplastics. And you saw Roberto put the pyramid of materials up there, and you see the high performing ones are typically high performance is governed by how high the glass transition temperature is, right? And that's why you see those used in applications like aerospace, where they need that temperature resistance. They want it for safety reasons if there is a fire. So we do have to think about applications where that might be an issue, and that could be a limitation on the use of thermoplastics. And of course, I was involved in developing this, and I'd love to see it used, but we have to acknowledge that fact, right?
Yeah.
So they're not going to replace thermosets in all applications. Any other questions?
I have question. What will happen when you put this material on an attack like the Twin Tower? How long do people have to leave the building? How long do people have?
So are you asking like if this was in a
they
structure, it's something, it
Yeah.
caught fire, how long is due?
Uh-huh.
That would really depend on the factor of the resin and things like it's in concrete. So there's always that heat transfer between the concrete to the rebar, then the elongation stuff, but that falls into let's just say there are ACI guidelines that would have to follow for all that type of stuff. Right now, this is really at like ground level. Realistically, we think, John, 5 to 10 years minimum before any real application, probably.
For what, thermoplastic?
Yeah, minimum.
Yeah, given the amount of footprint that the thermoset composites have had. But as was pointed out, there are a couple of benefits to thermoplastic rebar where it makes sense.
So it would be, it's time for like the thermoset rebar has been around for 2 decades, if not more now. And it just got codified in the building industry. So it takes time, there's research and things like that. So the answer to your question is, we don't know yet because it's way too early.
Correct, yeah. John, when you are talking about the ACI 440 code, I think you mentioned cover of the rebar. The
Right.
code was developed for thermoset rebars, specifically vinyl ester resin with glass reinforcement, and not for other type of polymers. I had a chance to talk to one of the researchers who was involved on that project, in fact, last week at another conference. And the plan is to have an addendum of the code for other materials, including thermoplastics. So the way to get these products, like the one we have seen in the presentation, it will be the next step is to get to this appendix of ACI 440 in the next version of the code, where that will be one issue to address. I mean, what will be the cover required for fire prevention when the bar reinforcement is made of a thermoplastic material? And as Bill mentioned, it will depend how high we are in that pyramid we have seen of thermoplastic polymers. I mean, what are the properties? So the final answer will be probably more in a matrix form, meaning what is the temperature that polymer will sustain? And for that type of polymer, what will be the cover required for fire performance?
So just as a comment to the question, when we were in the hearings for the 440 rebar code, we had fire provisions in the code itself in chapter 19, along with a very robust commentary about testing that has been done at Queen's University, University of Edinburgh. Dr. Bixby, Dr. Mark Green did phenomenal research towards that. So not that there would be additional cover, but there's additional coatings and stuff that can be put on structures to preserve the temperature to get the 2-hour fire rating that would be necessary, but that would have to be done on a case-by-case building official. However, during the hearings, it was originally rejected because we had some opposition from the epoxy-coated steel Institute. So those provisions were moved to commentary, recognizing in the next iteration, certain other things will be added to chapter 19 that makes that section much more robust. So here we had something that was validated, codified, and we still had resistance. So to make sure that the code got out into circulation, we had to move provisions to commentary, recognizing everything you need to know is there. So that is going to be up to the design engineer to make the question. but I also had a question.
Go ahead.
We spent a lot of time in the design equations in the 441R document and also in the 440.11 rebar code. When it comes to strength at bends, you know, one of the things that even the thermoset rebars always took a hit with was the bending of the fibers, because obviously when the fibers are perfectly aligned and in tension, they carry the greatest load. As soon as you bend it, there's a reduction in strength. So I know you haven't studied that yet, but that's going to have to be your biggest goal, is what is happening with the fibers in the bend. Are they buckling, and at what percentage of load is being decreased? Food for thought.
Yeah, and we are, one of the things we are planning on doing are development length tests, both with straight and bent bars, right? And I think those knockdown factors, John, are what they're on the order of 50% or something like that. Depends on US code and Canadian code are a little different. I think, Roberto, that might ring a bell for you too, like that 50% or so. But yeah, we recognize that hook bars and bent bars, absolutely. But I wouldn't anticipate these being any worse than thermosets. Any other questions out there? Joe, I have one practical one for you here. I had to jot a few down. I know that, so I typically, correct me if I'm wrong, MaineDOT is often mixing straight FRP rebar with bent stainless steel bar in the same deck because of the challenges of getting bent thermoset FRP rebar. So how does the cost compare between straight up thermoset FRP now and stainless steel? I know it may vary in time, but I'm just curious.
So the other kicker is why we do stainless steel on the curbs is crash ratings. So the bridge rail and everything was designed with a mild steel reinforcement. You can extrapolate that with the stainless steel or a 1035 high carbon, but not all that testing and evaluation has not been done with GFRP. And since GFRP is modulus elasticity's orders of magnitude lower than steel, it's so linear elastic that once it goes, it doesn't yield. That also plays into effect. It's not just the constructability, it's the actual designed engineered system of a bridge rail. We have used it in medium barrier. So back to your question on that one, Bill. Rebar tends to be, so glass bar itself is not a pound per pound item, it's a per linear foot item. So the best way to describe it is 1 pound of number 5 bar is about a foot long just because of the weights. So it's roughly anywhere between $1 and $1.25 per linear foot of bar, depending who's bidding it and where it's coming from, which puts it about on par with a standard, with a galvanized or epoxy bar. Black bar is a little bit less these days. As far as stainless goes, due to certain world events, the price of stainless went through the roof. And at that point, MaineDOT transitioned to the 1035 bar, so the Chromex. And we've been using that ever since. And that's coming in somewhere around 150% more than glass bar, but it's still 100-year service life. It still can be bent. It's still readily available. We get it out of New York. So does that answer your question?
Yes, yes. It's always good information to have. And that illustrates that we're in a realm here with the GFRP rebar, thermoset, thermoplastic, where it is very cost competitive, basically, on a first cost basis. Tim, you haven't got any questions yet. Life's been easy for you over there. So I noticed on Loutz's Creek that you had the splice. And of course, Roberto and I are very interested in the splice, right? Is that the only spliced arch you've done so far?
That is the only spliced arch.
The first one that's gone out there. Yeah, but it went well, right?
It did, yeah. The contractor essentially had a laydown area of flat ground that they could, we essentially we infused the full arch all at once. And so when we cut it in half, it was actually fully infused for the full geometry, cut it in half, and then pre-inserted 1/2 of the splice into one tube, and then drilled locator holes in the shop so that they could essentially just insert a locator pin into those locator holes, and that would align the spine of the arch
continuously, and then they erected it. And it was, I mean, our portion of install for the 12 arches and the decking and the concrete infill was 6 days. So it wasn't a hang up on the overall, schedule of the project to have that added field displays.
Nice. Internal reinforcing cage in there.
Internal reinforcing cage for, the long-term durability of that connection, and the added FRP field splice is really just for the stay in place form during the casting of the concrete.
Right.
Yeah.
Excellent. Okay, well, any other questions? Yep. Oh, 5-minute warning back there. I guess I thought you had 5 questions. I guess not. Okay, well, we're right on time. And I think we can go ahead and close out today or this week's conference. I'd really like to thank everybody for attending this year, in particular